far we have discussed the Heisenberg and Schrodinger pictures of quantum mechanics, and what I have shown you is that both are equivalent, both are equivalent, and in Heisenberg's picture things are defined through matrices, and in the Schrodinger picture we have the wave function, and when you want to define a quantity x for p, it is done through operators for each quantity. So, we had, for example, x m n matrix element of Heisenberg picture as psi m star x operator on n dx, and when this operator x operator acts on psi n, this means it just multiplies by x psi m star x times psi n x dx. On the other hand, we also defined p m n, which was equal to minus infinity to infinity psi m star p operator acting on psi n dx, and p operator, when it operates on psi, is a differential operator. So, it actually differentiates it. So, you get psi m star h cross over I d psi over dx dx. And then we also defined the expectation values for these quantities. So, expectation value for x and expectation value of p were defined as minus infinity to infinity psi x square x dx, and expectation value for p was defined as the integration over psi star h cross over I d psi over dx integrated over. And we also understood these as the average values of these quantities. Not only that, we could also see that operators corresponding to p square was nothing but p operator square, and this became minus h cross square d2 by dx square. Operator corresponding to x square was nothing but x square multiplying the wave function. And similarly, we can define higher powers of these operators and also their own multiplication. What we are going to learn in this lecture through all this is a very important principle of quantum mechanics known as the uncertainty principle. Which states that quantities in quantum mechanics cannot be measured in general with very high precision. In fact, two quantities which are called conjugate to each other have a relationship given by uncertainty relation. If you measure one quantity to very high accuracy, the other quantity becomes less accurate, and that is what we are going to see why it happens in quantum mechanics. It actually is a result of the quantum condition, and therefore, this is a principle which is very unique to quantum mechanics. You may have learned about uncertainty principle in your 12th grade just as a statement. So, let me just write it and then we will explore it further. You may have learned that for a given particle delta x delta Px is greater than or equal to h cross by 2. So, what does it mean? How do we define delta x? How do we define delta Px? We are going to see it in a mathematical rigorous manner in this lecture. So, let us see, if I am making a measurement of quantity x, then I do get an average value x, and if I measure x square, I get an average value of that. If I subtract expectation value or average value of x from this and take square root, this is defined as delta x. Similarly, if I take p square, expectation value of that, subtract the square of the expectation value of p and take square root, this is delta p. In general, and let me write it on the right hand side, in general, for any quantity, right, let us call it O or operator O, the uncertainty in O will be equal to square root of O square expectation value minus expectation value of O squared, and that makes perfect sense. Let me explain how so. Suppose I have a quantity, or say take some numbers, let us say I measure and I get 1, 2, 2, 3, 1, 4 and so on. Let us restrict ourselves to 1, 2, 3, 4, 5, 6 numbers and take the average. So, let us say this is x. The average will be 1 plus 2 plus 2 plus 3 plus 1 plus 4 divided by 6, and that comes out to be 8 plus 5, 13 over 6, roughly 2, and therefore, x square is roughly 4. Let us take x square average, and that comes out to be 1 plus 4 plus 4 plus 9 plus 1 plus 16 over 6, which is nothing but 5 plus 4 9, 18 plus 16 34 plus 35 over 6, which is roughly 6. So, you see, average of x square is greater than x square, and therefore, two are not the same because there is a spread in the values. On the other hand, if all x's were the same, then these two would have been equal. So, what this delta x or delta p or delta o in general gives you is the spread in any quantity. If I make several measurements and find that they are different, this delta x defined in the manner given here gives me how much is the spread. And what uncertainty principle tells you is that this spread multiplied by the spread in the conjugate quantity is greater than h cross by 2, and let us now show that. So, before that, I just want to tell you what happens for an eigenvalue in terms of a spread. So, for example, suppose I have an operator O which operates on a wave function psi and gives me the eigenvalue O n psi n. Then the expectation value of O will be given by integration psi n star O psi n dx, which is nothing but O n, which comes out, which is a number, psi n star psi n dx, which is O n. On the other hand, if I calculate O square, this will be integration psi n star O square psi n dx, which is nothing but O n comes out, you are left with psi n star O operating again on psi n dx, and you get O n square integration psi n star psi n dx, which is O n square. So, in this case, what you see is that O square is same as expectation value of O squared, and therefore, delta O is 0. So, if I take the expectation value of an operator with respect to the wave functions that are its eigenfunctions, and then calculate the spread in it or delta x or delta O in it, it comes out to be 0. Therefore, in stationary state, we can write right away, in a stationary state, delta E will come out to be 0. It is a fixed energy state. All right. So, with this background, I am now going to prove the uncertainty principle. For that, I need something called the Cauchy Schwarz will be SWA inequality, which if I simply put in terms of vectors, it says nothing but A dot B magnitude is less than or equal to magnitude of A and magnitude of B product, which is very easy to understand because A dot B is nothing but magnitude of A, magnitude of B times cosine of theta, and this is always less than or equal to mod A mod B product, because cos theta mod is always less than or equal to 1. In terms of functions, what it tells you is, if I have an operator O1 and its product with O2 and take its expectation value, what that means is I am taking psi star x O1 operator O2 operator psi x dx, this and take its modulus, this would be less than or equal to the individual expectation values, that is psi star O1 psi dx times psi star integration O2 psi dx, which is nothing but, this whole quantity is nothing but expectation value of O1 and expectation value of O2. This is known as the Cauchy Schwarz inequality, and we are going to use this now to prove the uncertainty principle. For that, I choose the quantity x minus mod x as one operator. So, this is going to be O1 and O2 is going to be this operator P minus expectation value of P. So, I am going to have from Cauchy Schwarz inequality. So, I am going to use the Cauchy Schwarz inequality and take the, so what I am going to show is that take x minus mod x and P minus, not expectation value of P, expectation value, and this should be less than or equal to expectation value of x minus x square square root times square root of P minus mod P square. You may wonder why I am taking this square root, because you see expectation value of x minus mod x is 0 and expectation value of P minus expectation value P is 0. So, what I am really actually calculating is this spread or delta x delta p on the right hand side. This is kind of RMS deviation. Let us work on the left hand side. So, expectation value of x minus expectation value x p minus this quantity is nothing but expectation value of x p minus x p average minus x average p plus x average p average, and I am taking expectation value of this, which is nothing but expectation value of x p minus x p minus x p plus x p, and I am going to cancel a few terms. So, this fellow cancels with this, and I get this equal to expectation value of x p minus x p. In all this, keep in mind that whenever I am writing this angular bracket or the expectation value, that is a number, all right. So, this quantity is a number and this quantity is a number. If you are uncomfortable in using x minus expectation value of x and p minus expectation value of p, expectation value as less than equal to square root of x minus x expectation value square expectation value times square root of p minus expectation value of p square expectation value, then you can instead use for O1 this itself square, and for O2 the square of p minus p expectation value square, and write the Cauchy Schwarz inequality as x minus mod x square p minus mod p square expectation value would be less than or equal to x minus expectation value of x square expectation value times the expectation value of p minus p expectation value square expectation value, leading to the same result as derived earlier. So, we have calculated x minus x p minus p expectation value to be expectation value of x times p minus x p expectation value product. I am going to use this and do a trick. I will write this as x plus p x expectation value divided by 2 plus x p minus p x expectation value divided by 2 minus x p. So, what have I done in this? What I have done is I have written x p product as x p plus p x divided by 2 plus x p minus p x divided by 2, and when I take the expectation value on the two sides, this is what I get, and I have used this here and here. This then I know is nothing but expectation value of x p plus p x divided by 2 plus, recall from the quantum condition that x p minus p x is nothing but I h cross. So, therefore, this becomes I h cross by 2 minus x p. Now, I leave this as an exercise for you to show that expectation value x p plus p x is real. All right. This is very easy to show if you write p in the operator form. So, this actually becomes integration psi star x times h cross over I d psi over dx plus h cross over I d over dx of x psi dx, and you can do the manipulations, you can do integration by part and show that this comes out to be real. So, what you have is that x p expectation value is expectation value of x p plus p x divided by 2 plus I h cross divided by 2 minus x p, which is real quantity A plus an imaginary quantity h cross by 2, where A is defined to be x p plus p x divided by 2 minus x p. So, to collect all this together, what have we done? We have found that expectation value x minus mod x, p minus mod p modulus is less than or equal to delta x delta p, which were defined as, let me remind you, delta x was defined as square root of expectation value of x square minus mod x square, and this was defined at square root of x p square minus p square, which was nothing but, let me also write this as x minus expectation value x square expectation value. Same thing for the other term, this is nothing but p minus expectation value of p square expectation value. They are all one and the same thing. So, on the right hand side I have delta x delta p, which is defined through all this operations, and on the left hand side now I have modulus of A plus I h cross over 2. So, what do we have? We now have the modulus of A plus I h cross by 2 is less than or equal to delta x delta p. Modulus of A plus I h cross by 2 is nothing but A square plus h cross square by 4 square root, which is certainly greater than h cross by 2, because A square is a positive quantity, and therefore, from here I have my result that h cross by 2 is less than or equal to delta x delta p, and this is the uncertainty principle, which says that if you measure for a wave function x many times and p many times, there will be a spread, but the spread is going to be such that its product will be greater than or equal to h cross by 2. It is not a limitation of your measurement, but this is fundamentally inherent in quantum mechanics. I had alluded to it, I had hinted about it when we constructed a wave packet for a particle few lectures back, and what I had said there, that if I have a wave packet which has a spread of delta x, the corresponding mixture of plane waves that gives you this has delta k spread in k space, such that delta x delta k is of the order of 1. You multiply by h cross on both sides, you get delta x delta p of the order of h cross. So, the moment you try to represent a particle by a wave, you get this sort of uncertainty relationship, because the moment you try to show it as a wave, it cannot be localized to the accuracy which you wish to have. There is a limitation, and then the momentum also gets a spread correspondingly, and which is given by this uncertainty relationship. You can see if I make delta x smaller and smaller, delta p x becomes larger and larger. If I make delta x larger and larger, delta p x becomes smaller and smaller. So, this is the kind of relationship that these two spreads have. As I said earlier, the wave functions that are eigenfunctions do not have a spread. So, let us ask a question. Are there wave functions that have either delta x equal to 0, and these will be the eigen functions of x operator, or delta p equal to 0, and they will correspond to eigenfunctions of P operator. So, you can physically think that for eigenfunctions of x operator, x times this f x should give you a definite x 0. And the only way it can happen is if f x is delta x minus x 0. This also, if you recall from previous lectures, is nothing but 1 over 2 pi integration e raised to I k x minus x 0 dk. Since the amplitudes of all plane waves are the same, that means all momenta come with the same probability. So, you can see that delta p, this representation gives you that delta p is infinite, whereas delta x in this case is 0. So, the product kind of remains finite. How about eigenfunction of P operator? For this, I am going to have h cross over I d psi over dx, which is the P operator operating on psi, is going to be a definite momentum P psi, and this immediately gives you that psi is e raised to I p x over h cross. So, what I have shown you is that eigenfunction of P is e raised to I p x over h cross, which I can write as e raised to I k x. This has value of momentum for a particle in this state is p fixed. On the other hand, this is a plane wave. So, it goes all the way from plus infinity to minus infinity. So, delta x tends to infinity in this, whereas since this momentum is fixed, delta p is 0. These are two ideal cases. In one case, the wave function is a delta function. In the other case, wave function is a plane wave spreading from minus infinity to infinity. And for a particle, these are two ideal cases, two extreme cases which are not seen. What is seen is, for example, particle in a box, where the wave function is between 0 and L. Or you also see the particle in a simple harmonic motion potential, where if this is the potential, the wave function is like e raised to minus x square. So, it has some spread, and this is where delta x is not going to be 0 and delta p is not going to be 0, but the product will always be greater than or equal to h cross by 2. Similarly, in particle in a box, delta x is not going to be 0, delta p is not going to be 0. In fact, I am going to give you the problems in the assignment where I would ask you to calculate delta x and delta p for these, and see what their product is. It should always come out to be greater than h cross by 2, as we have seen rigorously in our derivation. So, what you have learned so far is the uncertainty principle, and I have confined myself to one dimension, which says delta x delta p x is greater than or equal to h cross by 2, and it comes in very handy for quick back of the envelope calculations. For example, now I know that delta x going to 0 means delta p goes to infinity, and recall from the previous lecture, for a bound state p expectation value itself is 0. So, delta p going to infinity means that p square expectation value is becoming very large, and this implies that p square over 2m is becoming very large. So, if you confine a particle more and more, its kinetic energy tends to increase because of the uncertainty principle. If you let it spread, it tends to become smaller, and you have seen this earlier. Again, we go back to particle in a box problem, where a particle was confined in a box of length L, and if you recall, this energy E n was proportional to 1 over L square. So, as L becomes larger, the energy becomes smaller. This is precisely a demonstration of uncertainty principle. We can use it also to estimate energies of different systems. For example, again I will go to the example 1 for using principle for estimating ground state or lowest energy of a system. So, first example I take is this particle in a box of length L, and you can see in this case delta x is of the order of L, and delta p, which is defined as square root of p square minus expectation value of p square, is nothing but square root of p square, because for bound state expectation value of p is 0. So, delta p, which is equal to square root of p square expectation value times L, is going to be greater than or equal to h cross by 2, and therefore, p square itself is going to be greater than or equal to h cross square over 4 L square. P square over 2 m, which is the energy, is going to be greater than or equal to h cross square over 8 m L square, which you indeed find is the case. As a second example, I will take the particle in a simple harmonic potential, and in this case, if this is centered at x equal to 0, I know the expectation value from symmetry of x is going to be 0, and let me assume that x square root is of the order of a, so that we can write the potential energy as 1/2 k a square, which is 1/2 m omega square a square. How about the kinetic energy? Now, again p expectation value is 0, therefore, square root of p square minus p expectation value square, which is same as square root of p square, is going to be of the order of h cross over 2 a, which is nothing but h cross over delta x, and therefore, the kinetic energy is going to be p square expectation value over 2 m, which is h cross square over 8 m a square, and the total energy E is therefore going to be h cross square over 8 m a square plus 1/2 m omega square a square. And to find the lowest energy, I minimize this energy with respect to the only parameter that is available to me, and that is A. So, I do dE over dA is equal to 0, which gives me h cross square over 4 m a cubed with a minus sign in front plus m omega square a is equal to 0, or you solve this, you get a square is equal to h cross over 2 m omega. So, what we have found by minimizing energy with respect to A, that A square is h cross over 2 m omega, and the total energy E was given as h cross square over 8 m a square plus 1/2 m omega square a square. This will come out to be h cross over 8 m times 2 m omega over h cross, so h cross square plus 1/2 m omega square times h cross over 2 m omega, which comes out to be h cross omega by 2. It's precisely the same answer as we got by solving the Schrodinger equation. So, let me comment here, since the minimum energy is the same as by solving the Schrodinger equation, the uncertainty delta x delta p for the ground state of simple harmonic motion should also be minimum. For all other states is going to be greater than h cross by 2. So, this is an application to get an order of magnitude estimate of the energy using the uncertainty principle. I will also give you some problems related to this in your assignment. So, with this, let me conclude this lecture by stating that delta x is the expectation value of x square expectation value when you subtract delta x from this and take square root. This is how we defined delta x. Similarly, if I take p square expectation value and subtract the square of expectation value of p, this is how we define delta p, and using the quantum condition along with the Cauchy Schwarz inequality, we got delta x delta p to be greater than or equal to h cross by 2, and that is the uncertainty principle. And then we applied it to estimate energies of two systems.